The magnitude of K will tell you if you have more products than reactants or if you have more reactants than products. And it's kind of a general kind of rule. It's not super specific. And sometimes I've had huge Ks that didn't really have that much more products than reactants, but it does give you at least a ballpark figure as to what to expect. So if you have a K that's greater than 1, you will have a product-favored reaction. The product dominates at equilibrium. So since you have more product over a reactant, product over reactant will be greater than 1. That's what having a K value greater than 1 is. On the other hand, we're going to see a lot of Ks that are much less than 1. That means you have more reactants around than products. Your reactant will dominate at the equilibrium. So literally, the number you get for K, if you got a K of, say, 70, well, 70 is greater than 1. That means you have a product-favored K. You're going to have more products than reactants. On the other hand, you calculate a K of 0.017. Well, that K is less than 1. That means you'll have more reactants at equilibrium than products. This is an example of a reaction which is very product favored. That K is much, much, much greater than 1. This is how they make ammonia, all right? And it's very product favored, and we know that as chemists because your K, 3.5 times 10 to the 8th, is just huge. It's much, much, much greater than 1. So numbers greater than 1 mean product favored. And so when that equilibrium hits, you're going to have more ammonia, NH3, than you'll have nitrogen and hydrogen. You can have Ks less than 1 too. This is the K for silver chloride breaking up into silver plus and chloride ions. And the equilibrium constant K with products divided by reactants would be silver plus times chloride divided by 1 because we don't include solids and liquids in the equilibrium. Well, this K is 1.8 times 10 to the minus 5. That's very, very small. So this reaction is reactant favored. So for the silver chloride, we should see more of the white silver chloride solid, then we would see the dissolved ions, if you will. But again, the important part, K is less than 1, reactant favored, K is greater than 1, product favored. These two graphs show the progression of some kind of chemical, and you can see the first one there on the left, the products is quite a bit higher than the reactants. So that means we have more products than we have reactants. That's a product-favored reaction. K should be greater than 1 for that case. On the other hand, the second graph there shows how reactants, when they stabilize, reactant concentrations are higher than products. So in these cases, you're going to have an equilibrium constant less than 1. That's going to be a reactant-favored condition. In this question, we have two equilibria. Two NO2s are in equilibrium with N2O4. K is 180. The second reaction is iron 2 hydroxide as a solid in equilibrium with iron 2 plus and 2 hydroxides. And it wants to say which reaction is true. So the first one says both reactions are product favored. Well, the first one is K of 180 is certainly greater than 1, so that's going to be product favored. But the second one is certainly not. That K is much less than 1. That's very reactant favored. So that's not going to fly. We have one product favored, the first one reactant favored, the second one. So A is out because both reactants are not product favored. B is out because both reactions are not reactant favored. K, the first one, is greater than 1, so it's product favored, but not the second one's reactant favored. So then it says C, reaction A is product favored and reaction B is reactant favored. That sounds good to me. That's like saying K of the first one is greater than 1 and K of the second one is less than 1. That's what we see. Answer C is the correct answer. Now, earlier I said how our textbook likes using Q a lot more than I do. So let's talk about what Q is, at least in the classical sense. Q is really helpful to chemists if you're not sure you're at equilibrium or not. And I think that's why the textbook authors became kind of obsessed with using Q all the time instead of K, because how do you know? And there's something to be said for that. However, in our Chemistry 223 class, Q will be used to kind of compare to a known value of K to see if you're at equilibrium or not. Q is described exactly as K. It's products over reactants, so big C and big D divided by little a and little b, and all of those letters are raised to their stoichiometric coefficients. But here's the thing, it's got the same form as K, so if Q and K are the same number, your system's at equilibrium, and you're good to go. On the other hand, if Q is not the same as K, that means your system is not at equilibrium, and you can make predictions as if you're going to have more product or more reactant. Here's kind of a visual image of how to compare Q and K. So in the middle part there, Q and K are the same value. Q is red and K is blue. And you can see they're the same number. So if Q and K are the same, your reaction's at equilibrium and you're good to go. However, what Q is used mostly for is to see if you are at equilibrium or not. And so you have to have a K value to compare your Q to. And if Q is less than K, it means that Q wants to become more like K. Q's going to have to turn a lot of your reactants into products. So if Q is less than K, we will say that the reaction should shift to the products, to the right-hand side. On the other hand, once in a while, we'll see that Q is a number greater than K. That means usually that you're starting from the product side and the products are breaking down to reactants. But either way, if your Q is greater than K, what that means is you're going to have a shift to the reactant side. You have to turn some of those products into reactants for equilibrium to kick in. That's going to be what happens when Q is greater than K. So notice the right and the left there. Q less than K means it's going to shift to the products, and a shift to the products means a shift to the right, because products are almost always on the right side. That's where we're using it. On the other hand, Q is less than K. That means you're going to have a shift to the reactants. Products are going to have to make reactants. That's called a shift to the left. So right and left are used a lot in chemistry. Right means towards the products. Left means more towards the reactants. So here's an example of how we can use reaction quotient Qs. The important part that I always find is that you can tell if you're at equilibrium or not. So this is the N-butane to isobutane equilibrium we mentioned earlier. And I'm just going to abbreviate isobutane as iso and the N-butane as N. But anyway, this reaction has been studied and its K value established at 2.50. So that means you have more products than reactants because K is greater than 1. Maybe it's not super big, but it's going to be a lot more products, or it's going to be a little bit more at least products relative to reactants. So let's say that we're doing this reaction. We measure the chemicals. Iso concentration is 0.35 and the N-butane concentration 0.15. Are we at equilibrium? If we're not at equilibrium, which direction will it shift? Will we have more products being formed and less reactants, or will we have more reactants and less products? This is what I feel a Q is good for. So what we're going to do in this problem is we're going to literally figure out Q. It's going to be product, the isobutane, divided by the reactant N-butane. And we'll compare that number to the 2.50 established number, and we can from there predict if the reaction will shift to the right or the left. So in this problem, the iso was 0.35 moles per liter and the N-butane was 0.15. Products divided by reactants, there's no weird stoichiometry, etc., etc. Q comes out to be 2.3. Now that's close to, but not the same as 2.50. So in this case, what's going to happen is you're going to end up making more products. The reactants will shift to the product side and more products will happen. So this is how I like to use Q. Like you have an established equilibrium constant and you're trying to confirm if you're actually at that equilibrium or if you're not. Here's a similar kind of question. It's the N-butane isobutane reaction. The K is 2.5 and the N-butane is 0.02 and the isobutane 0.03. And the question says, is this reaction at equilibrium? Well, first of all, if it's at equilibrium, Q and K must be the same. And for this reaction, we have 0.03 divided by 0.02. That comes out to be 1.5. And 1.5 is certainly not the same as the established K value, 2.5. So we are not at equilibrium. Our Q is less than K. And if Q is less than K, you're going to make more products than you are reactants. Another way to say that is a Q value less than 2.50 would imply too much reactants. So this is kind of a cool way to get this around. But when you see this, it's pretty chill. Q is products divided by reactants, 0.03 divided by 0.02. Q comes out to be 1.5. Q is less than K. Reaction is not at equilibrium. Those numbers would be the same if you were at equilibrium. And we're going to shift to the right. You're going to have more products, the isobutane, than you have reactants, the N-butane. Nothing you can't do.